I'm going to focus today on the talk about the intrusive record of the Pontiac subprovince and try to link that with what is observed at upper crustal levels, gold mineralization, and metamorphism. Okay, so last time I showed this, this map. Like Isaac mentioned, we can, okay, so first thing is that the Pontiac is composed of large intrusive bodies. It can be divided in three different intrusive or intrusion parts. The first one are the opacitic gneiss, like they can split on that we believe are a basement. The second one in orange on this map are the sanukitoid suite. I'm going to show you the dates right after. And we can see that there is that large S-type granite that is called the Decel batholith. And I'm going to focus during this talk today about the magmatic history of that big body. So if we look at the plutonic record of the Southeast Superior, I took the David Moll and co-author database, and I divided basically according to the type of magmatism. So we can clearly see that within the Abitibi, the type of magmatism evolved from TTG magmatism toward the short timing or short duration of sanukitoid magmatism, and then through S-type granite. We dated in the Pontiac for the first time the opacitic gneiss. We obtained a nice date at 2760-ish that we believe represent the basement. We redated some of the sanukitoid plutons in the Pontiac. And we also tried to date the Decel batholith because it was really loosely constrained before. So we tried first to recover zygons, but it turned out that they were all metamic zygons, so we cannot use them. We decided to use monazite instead, and this is the distribution of the monazite dates within the Decel batholith. As you can see, there is a protracted record of the monazites within the Decel batholith, and we can clearly see that there are two different crystallization pulses. The first one is estimated at 2640, and the final one is estimated at 2620. One nice thing with that is that it's clearly, or it seems to be related to some gold mineralization that Michi presented yesterday that is happening at the upper crust or at the upper level of the system. So we wanted to dig a bit more on that, and this is what I'm going to show you today. Okay, so let's zoom out. And this is a compilation from Laurent et al. 2014. And they basically compile, or they basically showed that on every craton at the Earth's surface, the plutonic record evolved through the same steps, starting from a TTG magmatism to a short-lived sanukitoid magmatism, and finally to S-type magma that are represented by these white symbols on this diagram. Then I tried to look at the duration of S-type magmatism. Actually, it's not that easy. And many of the granite localities do not have good ages to constrain the duration of S-type magmatism. And in my opinion, so this is the compilation. So it varies from about 5 million years long to more than 100. And I think it's important for us to better constrain the duration of S-type magmatism to better or to get a better understanding of the thermal architecture of the crust at that time. So here we have the opportunity to evaluate the duration of one of the most voluminous S-type granites and decipher tectonic processes. And we also can get a better understanding of the thermal architecture and maybe dig or decipher the implication for fluid and regional metal endowments. So we tried zygon, it didn't work. We tried monazite, but now we're going to try garnet. Why garnet? Because this is a common phase in S-type granite. It can be dated using different techniques. It can be dated using uranium lead. It can be dated using samarium neodymium, for example, or lutetium hafnium. Usually from the literature, people have explained the presence of garnet in S-type granite to be either derived from the source as selective entrainment of metamorphic garnet that can have grown under subsoilus or be peritectic. Or they can crystallize directly from the S-type magma, from the perluminous magma. And in this case, they would be derived or controlled by fractional crystallization and accumulation processes. So overall, the nucleation, growth, and breakdown of garnet in this type of environment is largely controlled by the fractionation degree, pressure, temperature, chemistry conditions, and kinetics or growth rates of diffusion. But overall, they need to be assessed on a case-by-case basis. Luckily, we have some tools, and I'm going to show you some laser maps today. It has been used mainly for metamorphic garnet in metamorphic environments, so we decided why not to use them in S-type granite too. And you can end up with really beautiful idea of what's the distribution of some key trace element within garnet to evaluate intracrystalline diffusion, for example, or to evaluate the relationships between deformation and garnet growth. It's a semi-quantitative approach. It's in 2D. Takes not a long time to do, between 1 or 4 hours, depending on the garnet size, and we can vary the beam size. So it enables us to evaluate the diffusion and growth rates, evaluate the factors that are controlling the trace element supply during garnet growth and breakdown, and also to interpret the meaning of the lutetium hafnium date that we get. So just as a reference, this is one of Isaac Garnet. So it's from the Pontiac host rock. It's metamorphic garnet from the metamorphic or from the sediments. And I know it's a bit small, but as you can see, there are two clearly textural or chemical domains. There is a core that is represented by, for example, higher values in vanadium or lower values in chromium. A sharp transition toward the rim. So from that, we can derive a crystallization history and reaction in a PT space. Okay, so let's go back to the cell batholith. So for this study, I decided to look at different bearing or garnet bearing samples. Two are located in this area nearby the lac Flèche at Pluton, and one is located in the Malartic area. These are two examples in the field. So these are white granite. The amount of garnet varies between different samples, but they are all muscovite bearing and sometimes with a bit of biotite. I decided to select the three samples. Why? Because they all show different grain size despite having almost the same composition. So for example, this one is a medium grain size white granite. You can see that it's composed of quartz, K-spore, muscovite plage, and a tiny bit of garnet. Same for here, but the grain size is a bit coarser. And this one is almost like a pegmatite. So what we did is that we decided to map the garnet, and I'm going to show you more specifically some of these beautiful maps. As you can see from here, we recorded a really sharp zoning, and we are going to derive from processes from these maps. We can make assumptions from these beautiful features. Okay, so let's zoom in. We're going to start with the lutetium because this is of interest. We dated the garnet using the lutetium hafnium geochronometers, and we want to assess if the chronometer was diffused at some point or disturbed. Okay, so we have three different samples. As you can see, we have common features, including first a core with a nice inner core that is enriched in lutetium, a depletion toward the outer core, and then an overgrowth with oscillatory zoning. If we look here, it's a bit of the same. We have a core showing oscillatory zoning in lutetium, a transition, and then an overgrowth with, again, oscillatory zoning in lutetium. And it's the same in this one. It's less evident, but it's the same. We have a core, oscillatory zoning, and then a rim like that. So let's keep that in mind. We can also look at the zirconium content of garnet. Why it's important? Because we aim to link the timing of garnet growth to the timing of zircon growth. And this is quite spectacular. Again, we have a core showing an oscillatory zoning in zirconium and an overgrowth that is totally depleted in zirconium. The same for this one. We have a core oscillatory zoning decreasing from the inner core to the outer core, and then the overgrowth that is totally depleted in zirconium. So at the time of the growth of the overgrowth, there was no zirconium available for the garnet to be incorporated in. Same for this one. We can also look at the uranium content of garnet. Again, we see the same features. We see first a core with oscillatory zoning in uranium, and then a depleted overgrowth in uranium. It's the same for this sample, same for this sample. We can look at phosphorus content of garnet. Why it's important? Because we aim to link the timing of garnet growth between monazite, apatite that are phosphorus-bearing phases. And again, the story is like for the other elements. We have a pretty enriched, relatively enriched core and a depleted overgrowth. And it's the same mechanism, or it's the same observations for all the samples that are from different areas again. Finally, we can also look at the lithium content. It's not usually done, but we decided to give it a try, and actually it turned out that it's the same story with a core again and the depleted content, and we can think about linking the lithium-bearing phases, like for example muscovite in our system, with the timing of garnet growth. Again, during the growth of the outer part of the garnet, lithium was not available at that time. So if we sum up, we have two different chemical zones that are observed in every samples from different places, featuring a core and an overgrowth. The transition is sometimes partially broken core or partially resorbed core. We attribute the oscillatory zoning to be controlled by a competition between garnet growth rate and cation diffusion rate. And it's usually the case in a magmatic environment or fluid-rich environment. And we can also try to link the low lithium, phosphorus, zirconium, hafnium, uranium content of the overgrowth, and it supports that the overgrowth grew after or during the crystallization of monazite, apatite, muscovite, and zircon. Okay, so that's for the chemical content of garnet. Let's look at the new ages we got. So we dated garnet. It's a long process, involves a lot of chemistry. But those are the three new ages that we obtain. So those are isochrons. And we obtained first, for these two guys, new ages at 26, 65, 67. And we have a new age at 26, 56. So it's new, but in the region, this timing is kind of usual now. So I'm going to try to now link the metamorphic record, the magmatic record, and link that to the mineralization along the Kalila-Claddagh Lake fault. Okay, so if we look at the different ages we have, or different time constraints we have, in the Pontiac host rock, so in black you have all the lutetium, hafnium, garnet ages. Some of them are from Isaac work. We have UPB monazite at 26, 65, 67. We have zircon overgrowth that are exclusively in the sillimanite zone. And we have the final record of zircon overgrowth likely at 26, 30 something. Okay, so we're going to link that to the monazite record of the Dussel batholith. So you've seen that before on my first slide. So this is the monazite record of the Dussel batholith, again protracted with two crystallization pulses. This is the timing of sonic-heat-wave magmatism in the region, and those are the different timing of gold mineralization. These are derived from Mitch's work, and this one is the rhenium osmium date from Stéphane de Souza in Malartic. And on top of that, we can add the new Garnet LUHF date that I've just presented from the Dussel batholith. So from that, we can clearly see that first, the Garnet record the early stages or early history of the Garnet of the Dussel batholith development. We inferred that at that time, we were already melting at some point, at some depth, metasediments to produce voluminous S-type granite. But we can actually slice this entire figure in a couple of different time slices. So this is what I'm going to do in the next minute. So first we can look at this first record. This is recorded by subsoidus monazite in the Pontiac rock. This is recorded by some of the monazite grain in the Dussel batholith. And this is the rhenium osmium age. So we know that at that time, we were melting sediments at depth. We were growing garnet in the Dussel batholith, and some fluid was circulating toward the upper part of the crust because there was some mineralization dated at that time in the Malartic area. The second one is the garnet growth, the large pulses of garnet growth in the Pontiac rock. That is recorded in the stolite zone, kyanite zone, sedimentite zone, both in the Rouen and the Malartic areas, and also now in the Dussel batholith. The next one, and I think it's a major one, it's at 26, 40, 45. This is recorded by Zycon overgrowth in the metamorphic Pontiac group. This is where the largest crystallization pulses of S-type magma happened, and this is related to the main gold event in Val d'Or and Malartic. And I interpret that as a regional cooling of the system. So we were cooling down, we were crystallizing large amounts of S-type magma at that time, and this is also reflected by gold-bearing systems in the upper crust. The story ends up at, well, it's a bit shaky, but around 2605, 2620. And it's the final crystallization of the Dussel batholith recorded by the monazites. And it could also be coeval with what Michi and co-author interpret as a gold remobilization in the Val d'Or area. Okay, so if we go back to the model, and this is what Isaac just presented to you. So these are at two different times. So the first one is at 2667. So at that time, what we got, we were burying supracrustal sequences at depth. This is recorded by subsoidus monazite, okay, at the green schist to amphibole adfacious conditions, along a low gradient, a low pressure temperature gradient, or TOP. At the same time, we were producing some S-type magma. We were actually crystallizing garnet, okay? And at 2656, plus or minus 4 to 5, we were growing now garnet in the Pontiac along isobaric heating path and along thermal disturbance of the isotherms. And we were also growing garnet in the Dussel. After that, again, next step, it's cooling of the entire system at 26, 40, 45. That is recorded at different crustal levels. So from the middle crust to the upper crust and the mineralized system. So to conclude my presentation today, so we've seen that the trace element record in every garnet that we've tested is the same. So it looks like it's an ubiquitous mechanism for deformation. They feature a magmatic core with beautifully preserved trace element oscillatory zoning that we interpret as controlled by growth, garnet growth rate and diffusion rates of the cations. They feature an overgrowth that is seen to post Zycon, monazite, and muscovite. We obtain different lutetium hafnium garnet dates. Two of them are at 2665, and one of them is at 2656. The Garnet record the early history of the S-type magmatism in the region. We've showed that the crust stay at high temperature conditions for a long period of time. And this is supported by the protracted record of monazite from the Decel batteries for a period that we estimate to be around 50 million years long. It's consistent with crustal overturn, this type of long-lived high-temperature conditions. I interpret that major regional calling at 2645, which is by the way also recorded in the Abitibi province by the Lamotte batholith, for example, Lacorne Lamotte batholith. And we're in the process of testing what would be the implication for the fluid and metal endowment, and what are the relationships between what's happening at depth, at lower crustal level, and at upper crustal level. And this is where we are doing ongoing research on exposed lower crustal levels, such as the Capus casing uplift or the Grenville tectonic front that are just windows on lower crust at that time. So thank you for your attention.